Imagine standing at the threshold of impossibility. A spacecraft awaits, its hull gleaming against the cosmic backdrop. Instruments hum with barely contained power. The mission is defined by a single, audacious goal: to accelerate this vessel to the speed of light. The speed of light, that cosmic speed limit that separates the possible from the impossible, the real from the theoretical, the earthbound from the transcendent. At 186,282 miles per second, light travels further in 1 second than sound travels in 13 hours. Light from the sun reaches Earth in 8 minutes. Light from the nearest star takes 4 years. Light from the far edges of the observable universe has been traveling for billions of years. But what if you could match that speed? What if you could somehow, impossibly, accelerate a spacecraft with a human aboard to 299,792,458 meters per second, the absolute cosmic speed limit? The question seems absurd. Physics forbids it. Thermodynamics recoils from it. Yet contemplating it reveals truths about reality that reshape understanding. For in imagining the impossible journey at light speed, one encounters the deepest mysteries of existence. The nature of time, the structure of space, the relationship between motion and being. This is not idle speculation. This is the edge of Einstein's revolution, the frontier where relativity reveals that space and time are not absolute backdrops but malleable, observer-dependent, woven into the fabric of existence itself. What would happen to the traveler approaching light speed? What would they experience? What would they perceive? The answers are more profound, more strange, more beautiful than any work of imagination could conjure. They are rooted in the mathematics of space-time, in the geometry of reality itself. The journey at light speed is impossible for anyone with mass. Yet, in contemplating it, in pushing physics to its limits, humanity touches something fundamental about the universe and about consciousness itself. The questions that arise are not merely technical but existential. What does motion mean? What is time? What is space? What remains of identity when the very foundations of experience dissolve? Let us embark on this impossible voyage and discover what lies at the edge of the cosmos. For centuries, humanity assumed that the speed of objects was relative to the observer. Stand on a platform and watch a train pass at 100 kilometers per hour. To a person on that train, the platform moves backward at 100 kilometers per hour. To an observer on another train moving in the same direction at 80 kilometers per hour, the first train appears to move at only 20 kilometers per hour. Speeds add and subtract according to intuitive Galilean rules. This seemed obvious, grounded in everyday experience. The world operated according to simple, common-sense principles. Faster or slower, near or far, all depended on the observer's point of view. Newton's laws of motion reinforced this intuition. Space and time were absolute, universal, the same for everyone. Motion was relative. Space and time were not. Then came light. Physicists in the 19th century developed a comprehensive theory of light as an electromagnetic wave. James Clerk, Maxwell's equations, unified electricity and magnetism, predicting that electromagnetic waves should propagate at a specific velocity. The calculations yielded a number, approximately 300,000 kilometers per second. This matched the measured speed of light, suggesting that light was simply an electromagnetic phenomenon traveling through the fabric of space-time. But at what speed should light travel? According to Newton's framework, the speed of light should depend on the motion of the observer, just like the speed of a train. Light emitted from a moving source should be faster or slower, depending on whether the source moves toward or away from the observer. Yet experiments defied this expectation. The Michelson-Morley experiment of 1887 attempted to detect the ether, the hypothetical medium through which light supposedly propagated, by measuring whether Earth's motion affected the measured speed of light. The experiment found no such effect. Light always traveled at the same speed, regardless of Earth's motion, regardless of the observer's velocity. The result was puzzling, troubling, almost incomprehensible. It violated everything physics had learned about relative motion. How could the speed of light be constant for all observers? How could this be reconciled with Galilean relativity? The answer came from a young Einstein working in a patent office in Bern. In 1905, he published a paper on special relativity that revolutionized physics by taking the constancy of light speed as a fundamental principle. Einstein did not try to explain why light speed was constant. Instead, he accepted it as a given and explored its implications. If light speed is the same for all observers, Einstein reasoned, then time and space cannot be absolute. Two observers in motion relative to each other must measure distances and durations differently. For them to both measure the same speed of light, the very nature of space and time must change between reference frames. This insight led to the Lorentz transformation, equations describing how space and time coordinates transform between different observers. These equations predicted that moving clocks tick more slowly, time dilation. Moving objects appear shortened, length contraction. And most radically, simultaneity, the notion that two events occur at the same time, became observer-dependent. Events that are simultaneous for one observer might not be simultaneous for another. There is no universal present moment, no cosmic clock ticking at the same rate everywhere. Time is woven into space-time along with space, and space-time's geometry depends on the observer's state of motion. The constancy of light speed is not some arbitrary feature of the universe. Rather, it is a fundamental principle from which the entire structure of relativity emerges. Light speed is the cosmic speed limit, the speed at which causality itself travels, the maximum velocity at which information can propagate. Nothing with mass can reach this speed. As an object accelerates toward light speed, its effective mass increases due to relativistic effects. It becomes harder and harder to accelerate further. To reach light speed would require infinite energy, an impossibility for any finite system. But the question persists: what if you could approach that limit? What if a spacecraft could accelerate to 99.9999% of light speed? What would the traveler experience? The answer requires delving into the strange world of extreme relativistic velocities, where space and time behave in ways that seem to violate human intuition at every turn. The constancy of light speed is the foundation upon which all that follows rests. It is the cosmic principle that makes all the strange phenomena of relativity possible. It is the answer to the question of why motion at light speed is so fundamentally different from motion at any other velocity. And it is from this single, elegant principle that the mysteries of a light speed journey unfold. Imagine accelerating gradually to a velocity approaching that of light. The acceleration is subtle, almost imperceptible. Over days and weeks, the spacecraft's velocity increases. 50% of light speed, then 80%, then 99%. At each stage, something remarkable occurs. The traveler's clocks begin to diverge from Earth's clocks. At 99% light speed, time dilation becomes significant. For every year that passes aboard the spacecraft, approximately 7 years pass on Earth. The traveler ages slowly. A 5-year journey for the travelers corresponds to roughly 35 years of time passage on Earth. Friends and family left behind age rapidly from the perspective of the port. Traveler's reference frame. Push higher. Accelerate to 99.9% of light speed. Now the time dilation factor becomes more extreme. For every year aboard the spacecraft, roughly 22 years pass on Earth. A 10-year journey becomes 220 years on Earth. Approach 99.99% of light speed. For every year of subjective time experienced by the travelers, approximately 70 years elapse on Earth. The separation between personal time and cosmic time becomes staggering. At 99.999% light speed, the divergence becomes almost incomprehensible. A single year aboard the spacecraft corresponds to roughly 224 years on Earth. A decade-long journey spans more than 2 millennia on the home world. This is not a perceptual illusion. It is not a trick of time measurement. It is the deep structure of space-time itself. When an object moves at relativistic speeds close to that of light, the rate at which time flows for that object, as measured by a stationary observer, genuinely decreases. The mathematical relationship is described by the Lorentz factor, a quantity that depends on velocity. As velocity approaches light speed, this factor approaches infinity. Time dilation becomes more and more extreme. At light speed itself, the factor would be infinite, meaning that time would come to an absolute stop from the perspective of the stationary observer. But here lies a profound paradox that troubled physicists for decades: the twin paradox. Imagine two identical twins. One remains on Earth. The other travels in a spacecraft to a distant star at relativistic speed, then returns. According to special relativity, the traveling twin experiences less time passage than the stationary twin. When they reunite, the traveling twin has aged less. They are no longer the same age. This seems to violate the principle that relativity is reciprocal, that all observers in inertial reference frames are equivalent. From the traveling twin's perspective, couldn't they argue that Earth was moving away at high speed, and therefore Earth's clocks should tick more slowly? The resolution lies in recognizing that the traveling twin is not in a single inertial reference frame throughout the journey. To go to a distant star and return, the traveling twin must accelerate away from Earth, decelerate upon arrival at the star, turn around, accelerate back toward Earth, and finally decelerate upon arrival home. These accelerations are absolute. The traveling twin experiences gravitational effects during these phases. In special relativity, only inertial observers, those not accelerating, can claim that others' clocks tick slowly. The accelerating observer cannot make the same claim. The traveling twin's accelerations break the symmetry, making them the one who ages less. The twin paradox is not paradoxical once this asymmetry is recognized. It is a demonstration of a profound truth. Acceleration through space-time has real, measurable physical effects. Time itself flows differently depending on one's motion. This leads to a deeper question. What would it feel like to experience extreme time dilation? The traveler approaching light speed would not feel their clocks ticking slowly. From their perspective, time passes normally. They perceive the same duration of moments, the same progression of seconds into minutes into hours. But the outside world, planet Earth, the solar system, the galaxy would appear to age rapidly. Centuries would pass in what feels like years. Watching from the spacecraft, the stars themselves would appear to move faster. Supernovae would flash and fade in accelerated motion. The universe would appear compressed, accelerated, as if viewed through fast-forwarded film. For the travelers, time passes normally. For Earth observers, the travelers' clocks tick more slowly. Both perspectives are valid within their respective reference frames. There is no absolute truth about which clocks are really slower, only relative truths depending on the observer's point of view. This is the deepest lesson of special relativity. Time is not universal. Time is not the same for all observers. Time is relative, observer-dependent, woven into the fabric of space-time in a way that makes it inseparable from space. To travel at nearly light speed is to step outside the normal flow of time, to experience years while centuries pass elsewhere, to age slowly while the universe ages rapidly. It is to become a traveler not just through space but through the structure of time itself. As the spacecraft accelerates toward light speed, something equally strange occurs to the geometry of space itself. Distances contract. The universe appears to compress along the direction of travel. This phenomenon, called length contraction or Lorentz contraction, is a direct consequence of special relativity. Objects moving at relativistic speeds appear compressed along their direction of motion. An object that is 1 meter long, when traveling at 99.99% of light speed, appears compressed to roughly 1/70th of its original length, approximately 1.4 centimeters. This is not because the object is actually crushed. From the perspective of observers at rest with the object, it retains its normal size. But to a stationary observer watching the object move at near light speed, the object appears compressed. The universe experiences the same contraction from the perspective of the traveling spacecraft. Distances ahead, in the direction of travel, appear shortened. A star system that is 10 light-years away does not appear to be 10 light-years distant. The distance contracts. the far reaches of the cosmos appear to rush closer. At 99.99% light speed, a 10 light-year distance contracts to roughly 0.7 light-years. The stars, the planets, the intervening void, everything appears compressed, drawn nearer, as if the universe itself is shrinking around the spacecraft. This is not an optical illusion. This is genuine geometric contraction of spacetime as measured in the spacecraft's reference frame. If the traveler were to measure the distance to a distant star using instruments aboard the spacecraft, they would indeed measure a shorter distance than Earth-based observers measure. This contraction creates a profound effect on the experience of long-distance space travel. To a stationary observer, reaching a star system 20 light-years away would require traveling for at least 20 years at light speed, which is impossible since light-speed travel is unattainable, or much longer at speeds below light speed. The distance seems vast, insurmountable, but from the perspective of a spacecraft traveling at 99.99% of light speed, the distance contracts dramatically. The same 20 light-year journey might appear, to the spacecraft's instruments, to be only a few light-years. The journey's duration, as experienced by the travelers, might be only a few years, even though 20 years pass on Earth. This explains how the time dilation and length contraction work together. The universe contracts ahead of the spacecraft, drawing destinations closer. Simultaneously, time slows for the travelers, compressing the duration of the journey. The effect is that long interstellar journeys become accessible not in absolute terms, but in terms of the traveler's subjective experience. A journey to a star system 100 light-years away, at 99.99% light speed, would require 100.001 years to complete from Earth's perspective. But from the traveler's perspective, both time dilation and length contraction compress the experience. The distance contracts to roughly 7 light-years, and time dilation reduces the experience duration to roughly 7 years. The traveler experiences a 7-year journey, during which the spacecraft travels 100 light-years, as measured by Earth observers. The apparent contradiction resolves when one recognizes that different observers measure space and time differently. Both accounts are correct within their respective reference frames. The mathematical relationship describing length contraction is given by a simple formula depending on the velocity. At low velocities, the effect is negligible. At everyday speeds, objects do not noticeably contract. But as velocity approaches light speed, the contraction factor approaches infinity. At light speed, the universe in the direction of travel would contract to zero length. This means that a light ray, traveling at light speed, experiences the entire distance to its destination as zero length. From light's perspective, in the admittedly problematic sense of attributing perspective to a photon, it reaches its destination instantaneously, covering zero distance. This geometric contraction of spacetime is as real as any physical phenomenon. It arises directly from the structure of spacetime as Einstein described it. Lengths are not absolute but depend on the observer's motion. The universe is not a fixed stage with absolute distances, but a relative structure whose geometry varies with velocity. As the spacecraft accelerates toward light speed, the universe literally shrinks. Stars appear to draw closer. Distances compress. The cosmic gulf that separates Earth from distant worlds narrows. For the travelers, the universe becomes a smaller, more intimate place, not because the universe actually changes, but because the very geometry of space transforms at relativistic velocities. Beyond time dilation and length contraction, the experience of traveling at nearly light speed would bring extraordinary visual phenomena. The universe, as perceived from a relativistic spacecraft, would be transformed into something alien, strange, almost incomprehensible to the human senses. Imagine the night sky as viewed from Earth. Stars are scattered across the celestial sphere, their light having traveled to the observer from all directions. The Andromeda galaxy glows in the autumn sky. The Milky Way arches overhead. Constellations trace familiar patterns that humans have recognized for millennia, now accelerate to 99.99% of light speed, oriented toward a distant destination. The visual experience transforms dramatically. The phenomenon of stellar aberration occurs as the spacecraft moves. The apparent direction of distant stars shifts due to the spacecraft's motion, similar to how rain appearing to come from ahead when driving, even though it falls vertically. At relativistic speeds, this effect becomes extreme. Stars ahead of the spacecraft cluster toward the center of the forward field of view, concentrated into a narrow cone. The universe's width compresses. The full sphere of the night sky contracts toward the direction of travel, funneling into a brilliant point ahead. Simultaneously, stars behind the spacecraft, those in the direction it came from, disappear. They cluster together at a single point in the rear, becoming invisible as their light blue shifts and red shifts into wavelengths beyond human perception. The effect is as if the spacecraft is traveling through a tunnel of space, with the cosmos compressing ahead and expanding backward. The forward sky becomes brighter, more concentrated. The rear sky darkens, fades, eventually becoming completely dark as starlight from behind blue shifts beyond the visible spectrum. But this clustering effect is only part of the story. The Doppler effect, the change in frequency of light due to relative motion, profoundly alters the spectrum of starlight. Stars ahead of the spacecraft appear blue-shifted. Their light is compressed as they approach the spacecraft, the wavelengths shortened. The visible light from these stars shifts toward the blue and ultraviolet. A star that appears yellow to a stationary observer blue shifts to white. An orange star blue shifts to yellow. Red stars blue shift to orange. Simultaneously, stars behind appear, red shifted. Their light is stretched as they recede from the spacecraft. Wavelengths lengthened. Blue stars red shift to white. Yellow stars red shift to orange. Red stars red shift beyond the visible spectrum into infrared. The combined effect of aberration and Doppler shift creates a visual experience unlike anything on Earth. The forward sky becomes a brilliant, concentrated dome of blue-white light. The familiar star patterns are unrecognizable, compressed into this forward cone. Familiar constellations vanish or merge into each other. The surrounding sky fades. The rear sky becomes completely dark, devoid of visible starlight. The spacecraft travels through darkness, surrounded by a tunnel of blue-white light ahead. Furthermore, the Doppler effect shifts the frequencies of all electromagnetic radiation, not just visible light. Radio waves from distant civilizations would be shifted to higher frequencies. Cosmic microwave background radiation, the afterglow of the Big Bang, that fills all of space, would be blue shifted into visible and ultraviolet frequencies, potentially illuminating the spacecraft with an eerie glow. The spectrum of space itself would change. The cosmic microwave background, normally imperceptible to human eyes, would become visible as an intense glow concentrated ahead of the spacecraft, a shimmer, a halo of radiation marking the forward direction. There are additional visual distortions. Objects approaching or receding would appear distorted due to relativistic beaming effects. A planet or star system approached by the relativistic spacecraft would appear warped, compressed, as if viewed through a funhouse mirror. The effects of gravitational lensing, the bending of light by gravity, would also appear more pronounced at relativistic speeds. The overall effect is a profound transformation of the visual universe. The cosmos that greeted explorers aboard a relativistic spacecraft would be alien, unrecognizable, almost incomprehensible. The familiar night sky, that constant backdrop to human civilization since the earliest humans gazed upward, would vanish, replaced by phenomena that defy everyday intuition. In contemplating these visual effects, one confronts a fundamental aspect of relativity. The universe appears different to different observers. There is no single, universal appearance to reality. Reality's appearance is relative to the observer's state of motion and gravitational field. The traveler at relativistic speed would not see the universe as it truly appears, because no such universal appearance exists. They would see it through the lens of special relativity, through the distortions of time dilation, length contraction, aberration, and Doppler shift. Their view would be no less valid, no less real, than Earth-based observations. It would simply be a different perspective on the same underlying physical reality. The journey toward light speed encounters a fundamental barrier. It is impossible for anything with mass to reach light speed. This is not a limitation of current technology or future engineering. It is a fundamental principle of physics, grounded in the structure of space-time itself. The reason lies in the relationship between energy, mass, and velocity. As an object accelerates, it gains kinetic energy, energy associated with its motion. At low speeds, this relationship is simple and familiar. A car accelerating from 0 to 100 kilometers per hour gains a specific amount of kinetic energy proportional to the square of the velocity. But as velocities approach that of light, special relativity transforms this relationship. The energy required to increase velocity does not increase linearly, but exponentially, approaching infinity as velocity approaches light speed. Einstein's famous equation relating energy and mass, E equals mc squared, provides insight into why this occurs. The total energy of an object includes both its rest, mass energy, and its kinetic energy. As an object accelerates, its kinetic energy increases. But in special relativity, increasing an object's energy is equivalent to increasing its inertia, its resistance to further acceleration. An object moving at 90% light speed has a relativistic mass, an effective inertia that is more than twice its rest mass. At 99% light speed, the effective mass is more than 7 times greater. At 99.9% light speed, the effective mass is more than 20 times greater. To accelerate an object further requires pushing against this increased inertia. The closer the object approaches light speed, the more massive it effectively becomes, and the more energy is required to accelerate it further. At light speed itself, the effective mass would become infinite. An infinite force, acting on infinite mass, would be required to accelerate the object. This is physically impossible. Infinite force and infinite energy do not exist in the universe. Therefore, nothing with mass can be accelerated to light speed. It is not merely difficult or expensive. It is physically impossible. The barrier is not a limitation of engineering but a fundamental law of nature. This raises a deep question. Why is light speed special? Why is it the cosmic speed limit? The answer lies in the structure of space-time itself. Light speed is not merely a very fast velocity. It is the speed at which causality itself propagates. Information cannot travel faster than light. Causes cannot reach effects faster than light. The cosmic light cone, the set of events that can causally influence a given event, is determined by light speed. If objects could exceed light speed, causality itself would break down. Observers in different reference frames could disagree about which event caused which other event. Causes could occur after their effects. The fundamental logical structure of time would dissolve. To prevent this logical catastrophe, nature imposes a cosmic speed limit. No, information can travel faster than light. Nothing with mass can reach light speed. The universe is fundamentally causal, with the light cone defining the boundary of possible influence. Yet here lies a profound mystery. Why does such a limit exist? What is the deep reason that nature imposes this constraint? Some physicists propose that the structure of space-time itself, the geometry described by Einstein's equations, fundamentally requires this limit. Others suggest that at the deepest levels of reality, in quantum gravity's realm where space-time emerges from quantum information, the light speed limit has an even more fundamental origin. In any case, the limit is real. An object accelerated from rest, no matter how much energy is applied, will asymptotically approach light speed but never reach it. The gap between any achievable velocity and light speed is unbridgeable. This creates a profound constraint on space travel. The nearest star system, Alpha Centauri, is about 4.3 light-years away. A spacecraft traveling at 99.99% light speed would require more than 4 years to reach it, as measured by Earth observers. More practically, a spacecraft traveling at 10% light speed, an enormous fraction of the speed that current technology approaches, would require roughly 43 years to reach Alpha Centauri, still an enormous expenditure of time and resources. Yet here is where time dilation and length contraction offer a tantalizing possibility. From the spacecraft's perspective, the journey, duration, and distance both compress. A 43-year journey at 10% light speed would appear to the travelers, due to time dilation and length contraction, to last only a few years. The subjective experience of interstellar travel becomes feasible, even if it requires centuries from Earth's perspective. Thus, the unreachable limit of light speed paradoxically enables long-distance space travel. Velocities below light speed become practically useful when the provided relativity of time and space are accounted for. But reaching light speed itself remains forever impossible. The cosmic speed limit is absolute, inviolable, woven into the fundamental structure of space-time. To travel at exactly light speed is to encounter infinite time dilation, infinite length contraction, infinite energy requirement. The boundary is absolute. Light photons, the particles of light, are fundamentally different from anything with mass. A photon has no rest mass. It always travels at light speed, not because it is accelerating toward light speed and approaching it asymptotically, but because it cannot exist at any other velocity. For a photon, the question of what traveling at light speed is like takes on an entirely different character. What does a photon experience? This question treads into philosophical territory and raises fundamental questions about consciousness and perspective in physics. Technically, it is not valid to speak of a photon's perspective or experience, since photons are quantum entities and do not have the kind of localized perspective that macroscopic objects have. Yet there is something profound to be glimpsed by contemplating the photon's relationship to space-time. For a photon, time stands still. From the perspective of special relativity's mathematical framework, the time dilation factor approaches infinity as velocity approaches light speed. For a photon traveling at exactly light speed, this factor becomes infinite. According to the equations, zero time passes for the photon during its journey, no matter the distance traveled. A photon emitted from the Sun at 8 a.m. Earth time reaches Earth at 8:08 a.m., having traveled for 8 minutes according to Earth observers. Yet from the photon's perspective, or more precisely, according to the mathematical description of the photon's space-time interval, the journey is instantaneous. Zero duration passes. Simultaneously, length contracts to zero for the photon. The 8 light-minute distance from Sun to Earth contracts to zero length in the photon's frame. The photon travels zero distance in zero time to cover 8 light-minutes of space as measured by Earth. This is not paradoxical but mathematically consistent. The space-time interval A invariant quantity that all observers agree on is zero for light. Space-time appears degenerate from the photon's perspective, compressed to nothing. This reveals something profound about light's nature. Light is not an object moving through space and time like a bullet traveling through air. Light is fundamentally different. Light exists at the boundary between space and time, where the normal distinction between temporal and spatial dimensions becomes ambiguous. In quantum field theory, photons are not particles moving through space but excitations in the electromagnetic field. When an electron emits a photon, the electromagnetic field oscillates at a particular frequency and wavelength. The notion of where the photon is becomes meaningless. It is better understood as a propagating wave of field oscillation, an excitation spreading outward at light speed. Richard Feynman, the renowned physicist, noted that from one perspective, all electrons in the universe might be a single electron traveling backward and forward in time. Similarly, all photons might be manifestations of a single, vast quantum phenomenon extending throughout space-time. These are speculations at the frontier of physics, where quantum mechanics and relativity meet, and where the familiar notions of particles, motion, and time become ambiguous. What is clear is that light occupies a special place in the universe's structure. Light speed is the limit. Light carries information. Light defines causality. Light exists at the boundary of space-time, in a regime where the normal distinction between space and time, between past and future, becomes subtle and strange. For a photon, the question, "What do you experience?" cannot be meaningfully asked. There is no you, no localized observer, no moment-by-moment consciousness. Yet the photon's relationship to space-time existing at the light cone's boundary, covering infinite distance in zero time, hints at something profound about the universe's structure. Light is not bound by the constraints that bind matter. Light is free to travel at the cosmic speed limit. Light is the universe's messenger, the carrier of information across the cosmic void. In light's freedom lies the universe's structure, and in contemplating light's relationship to space-time, humanity glimpses something fundamental about reality itself. The cosmic speed limit of light speed has profound implications that reach far beyond theoretical physics into the practical questions of how humanity might explore the cosmos, communicate with distant civilizations, and understand the structure of reality itself. First, consider space travel. Current spacecraft travel at mere fractions of 1% of light speed. The fastest spacecraft humanity has ever created, the Parker Solar Probe, reaches velocities of merely 0.064% of light speed. Even reaching 1% of light speed would represent an enormous advance in propulsion technology. Yet, as discussed, achieving these velocities does not dramatically shorten cosmic distances from Earth's perspective. A spacecraft traveling at 1% of light speed would require roughly 4,300 years to reach Alpha Centauri. Even at 10% light speed, a speed that would require propulsion technology far beyond current capabilities, the journey would require 43 years from Earth's perspective. However, from the traveler's perspective, time dilation and length contraction provide a dramatic change. A spacecraft traveling at 99.9% light speed would experience a journey to Alpha Centauri lasting roughly 1/3 of a year. The cosmic gulf that seems insurmountable from Earth's stationary frame becomes traversable if enormous energy could be devoted to accelerating the spacecraft to near light speeds. This creates a peculiar asymmetry. A spacecraft crew could visit nearby stars and return to Earth within their subjective lifetimes, experiencing only a few years or decades of time. Yet hundreds of years would pass on Earth during their journey. The travelers would return to a future Earth unrecognizably different from the world they left. This is the reality of relativistic space travel. The cosmic distances are unchanged, but the relativity of time allows journeys that are practical for the travelers but consume vast stretches of Earth time. Second, consider communication. Radio signals, like all electromagnetic radiation, travel at light speed. A message sent toward a distant star takes years, decades, or centuries to arrive. A reply would take an equally long time to return. Meaningful, real-time conversations with distant civilizations are impossible if they are more than a few light years away. If an advanced civilization exists at Alpha Centauri, which is unlikely, but hypothetically, a message sent today would arrive in 4.3 years. A response would return after 8.6 years total. Multiple back-and-forth communications would consume decades or centuries. For stars thousands of light years away, in other galaxies beyond the Milky Way, communication becomes nearly impossible. The universe's immensity makes real-time contact fundamentally impractical. This raises a profound question about the nature of cosmic civilization. If intelligent species exist throughout the universe, separated by vast distances and enormous light travel times, can they meaningfully interact? Can civilizations build networks, share knowledge, coordinate activities, or does the cosmic speed limit enforce isolation, making each star system a universe unto itself? Third, and most fundamentally, the cosmic speed limit of light enforces causality. It ensures that causes precede effects, that information cannot travel faster than light, that the logical structure of space-time remains intact. But this raises a subtle point. Simultaneity is relative. Two events that appear simultaneous to one observer might not be simultaneous to another observer moving at high velocity. What constitutes the present moment depends on the observer's reference frame. Einstein's theory of relativity permits closed time-like curves, hypothetical loops in space-time, where one could travel into the past under certain extreme conditions, such as in the vicinity of rotating black holes. Yet these paths, while not strictly forbidden by the mathematics, would violate causality in ways that seem to lead to logical paradoxes. The question of whether causality is absolute or whether closed time-like curves are possible remains one of the deep open questions in physics. The cosmic speed limit, by preventing faster-than-light travel, appears to prevent the most obvious mechanisms for causality violation. Yet whether this prevents all causality violations remains unclear. These implications reach into profound philosophical territory. The cosmic speed limit shapes the structure of possible reality. It prevents faster-than-light travel. It limits communication. It enforces causality. It makes space and time relative rather than absolute. In contemplating these implications, one realizes that light speed is not merely a velocity in physics. It is a fundamental principle defining the structure of existence itself. The universe could not be radically different without changing this limit. Causality, communication, the very possibility of organized complexity all depend on light speed being the cosmic boundary it is. The thought experiment of traveling at light speed has captivated human imagination far beyond the bounds of physics. Science fiction authors have built entire universes around the possibilities and impossibilities of relativistic travel. Philosophers have used light-speed journeys as thought experiments to probe the nature of time, identity, and consciousness. In science fiction, many stories explore the theme of relativistic travel, creating asymmetries between travelers and stay-at-homes. A crew departs on a relativistic spacecraft, traveling centuries into Earth's future in their subjective experience of only decades. They return to find Earth transformed, civilizations risen and fallen, cultures and technologies unrecognizable. The human elements of this scenario, the psychological and emotional implications, have inspired countless narratives. Authors like H.G. Wells, with his Time Machine, and more contemporary writers explore the philosophical implications of time's relativity. If time is relative, if different observers experience different durations, what does this mean for identity? The traveler who ages only slightly while Earth ages centuries is fundamentally different from the stay-at-home. They are not merely separated by time, they have literally experienced different amounts of time. This raises questions about personal identity. Is identity tied to objective facts or subjective experience? If one traveler experiences 50 years, while another experiences 500 years, are they the same age? Or does age depend on the observer's reference frame? These are not merely semantic questions but probe the nature of selfhood and existence. Philosophers have used relativity to re-examine questions about the nature of time that troubled thinkers for millennia. Augustine wrestled with defining time. Aristotle grappled with whether time is real or merely a human perception. Kant treated time as an a priori category of understanding, a necessary feature of how humans perceive reality. Relativity reveals that these philosophers were asking questions about time's nature without realizing that time's nature is more complex than their frameworks allowed. Time is not absolute. Time is not the same for all observers. Time is woven into space-time and is relative to motion and gravity. Yet, in another sense, relativity deepens the ancient mystery. If time is relative, if it is emergent from space-time geometry, what is it fundamentally? What is time at the deepest level of reality? These questions have not been answered, but have been reframed by modern physics. Physicists have contemplated whether closed time-like curves, paths through space-time that loop into the past, might exist in extreme gravitational environments. Could one travel backward in time? The logic of relativity does not strictly forbid this. Yet doing so seems to lead to paradoxes. A time traveler could return to the past and prevent their own birth, creating logical contradiction. Some physicists propose that the universe is self-consistent, that even if time travel were possible, the laws of physics would prevent any action from creating genuine paradox. A time traveler attempting to prevent their birth would inevitably fail, through some chain of seemingly coincidental events. Others propose that time travel branches reality into alternate universes, avoiding the paradox by having the time traveler travel to a different timeline. These are highly speculative ideas, residing at the frontier of theoretical physics. Yet they arise from taking relativity seriously, from contemplating the deepest implications of light speed being cosmic limit. The thought experiment of light speed travel also illuminates the relationship between physics and human understanding. Physics describes reality using mathematics equations, symmetries, transformations, yet these abstract descriptions correspond to actual experiences, actual phenomena that would occur to real observers at relativistic speeds. The visual phenomena aberration, Doppler shift, time appearing to freeze, are not illusions or mathematical artifacts. They are genuine physical effects that would be observed. The universe would look different to a relativistic traveler. Their instruments would measure different values for space and time intervals. Their experience would be fundamentally altered by their motion. This connection between abstract mathematics and concrete experience is one of the deepest mysteries of physics. Why does the universe obey mathematical laws? Why do equations predict reality? How is it that humans, thinking creatures arising from cosmic processes, can comprehend the mathematical structure underlying existence? These questions touch on the nature of consciousness and reality itself. They suggest that consciousness and cosmos are not separate but are aspects of a unified structure. The human mind, evolved through cosmic processes, is somehow attuned to perceiving and comprehending the universe's mathematical order. In contemplating a light-speed journey, one encounters all these deep mysteries: the nature of time, the structure of space-time, the limits of possible experience, the relationship between mathematics and reality, the place of consciousness in the cosmos. To imagine traveling at the speed of light is to stand at the boundary of human understanding and experience. It is to contemplate what remains when the familiar structure of time and space dissolves. It is to ask fundamental questions about existence, meaning, and identity. The physical phenomena are remarkable. Time dilation that allows travel through cosmic distances, length contraction that shrinks the universe, visual effects that transform the cosmos into something alien and strange. Yet these physical phenomena point towards something deeper, something philosophical, even spiritual. For centuries, humans have wondered whether motion through space could be a form of transcendence. Travelers, explorers, adventurers have sought to escape the familiar, to venture beyond known boundaries, to touch something beyond the everyday. Space travel at relativistic speeds represents perhaps the ultimate expression of this ancient human impulse. Yet it also reveals a profound limitation. The cosmic speed limit is absolute. The traveler at near light speed cannot exceed it. Time does not flow backward. Causality is not violated. The traveler remains bound by the fundamental structure of space-time, no matter how fast they move. In contemplating light-speed travel, one encounters a paradox: enormous freedom and absolute constraint. The traveler can achieve velocities that seem godlike, approaching the fundamental cosmic speed limit. Yet they remain forever bound by that limit, unable to cross it, unable to escape the structure that defines reality itself. This paradox mirrors other fundamental limits in existence. Humans can raise consciousness to extraordinary heights through philosophy, art, science, and meditation. Yet consciousness remains bound by the biological substrate from which it emerges. Humans can expand their understanding enormously. Yet there are questions about their own nature, about consciousness itself, that may remain eternally mysterious. The cosmic speed limit is not a restriction imposed from outside. It is the structure of space-time itself. It is the universe's geometry. In accepting this limit, in understanding why faster-than-light travel is impossible, one accepts that the universe has a particular form, a particular structure that cannot be violated or transcended. Yet within this structure lies an almost incomprehensible freedom. Time dilation allows journeys through cosmic distance in personally manageable timeframes. Length contraction shrinks the universe's scale. The relativity of motion means that observers moving at different velocities experience genuinely different realities, and all these realities are equally valid. In traveling at near-light speed, one would experience something unprecedented in human history: genuine alienation from the ordinary flow of time. Centuries pass in personal decades, The universe transforms around the traveler while they experience only modest aging. They would return to an Earth transformed beyond recognition. This raises profound questions about meaning. Does a journey that transforms the entire world have meaning? Does the traveler's goal or discovery matter if centuries pass en route? Or does personal experience constitute meaning, regardless of external temporal scale? These are not merely intellectual questions. They probe the nature of human existence and value. They ask what makes life meaningful. Is it the duration or the quality of experience? Is meaning tied to objective facts about the universe or to subjective experience? Lightspeed travel forces these questions because it reveals that objective and subjective time are not the same. The traveler and stay-at-home experience genuinely different durations, yet they are experiencing the same universe. What constitutes meaning when observers' reference frames differ so radically? In contemplating these questions, one arrives at a kind of philosophical humility. The universe is stranger than human intuition suggests. Time and space are not the simple, unchanging backdrops they appear to be in everyday experience. The universe has hidden depths, structures that only reveal themselves when one pushes toward extreme conditions, toward light speed, toward gravitational extremes, toward the quantum realm. Yet this strangeness is not alienating but wondrous. It reveals that reality is far richer, far more intricate, far more beautiful than naive intuition grasps. The universe is not a simple stage with simple rules, but a complex structure governed by deep principles that humans have only begun to understand. The dream of traveling at light speed, even though it is physically impossible, has inspired humanity to contemplate the universe's structure, to develop theoretical frameworks of extraordinary power, to probe the deepest questions about existence and time. Perhaps the value of this impossible journey lies not in its achievement, which is forever impossible, but in the contemplation itself. In imagining light-speed travel, humanity confronts the fundamental limits and structures of reality. In asking what would happen, humans develop understanding about what actually happens and about the nature of existence itself. The universe has set a cosmic speed limit at light speed. Nothing with mass can exceed it. Yet by contemplating this limit, by imagining an impossible journey toward it, humans gain insight into the universe's deepest nature. The speed of light is not merely a velocity, it is a cosmic principle. It defines causality, enables communication, structures space-time, enforces the logical order of reality. In understanding light speed, in grasping why nothing can exceed it, humanity touches something fundamental about existence. And in that touching of the fundamental, in that glimpse of the universe's deepest structure, there is something transcendent. For in the limitations imposed by nature lies also a structure of almost incomprehensible beauty. The universe is bound by rules, governed by principles, woven from mathematics and light. To travel at the speed of light is impossible. To understand why is to begin to understand the universe. And in that understanding lies a meaning that transcends mere physical achievement, a meaning rooted in the human capacity to comprehend, to wonder, to reach toward the mysteries that define existence itself. The cosmic speed limit stands eternal. Nothing will ever reach it. Yet in contemplating it, in imagining the journey toward it, humanity reaches toward something infinite, the structure of reality itself, the fabric of space-time, the deepest mysteries of time and existence. And in that reaching, in that contemplation of the impossible, lies a meaning worthy of the infinite longing that has driven humanity to explore and understand the cosmos since consciousness first gazed upward at the stars.